All right, welcome everybody. Let's see, does anybody need one of these? Yep. Anybody else need feedback forms? All right. Thanks for being here today. My name's Isaac Wade. I am the instructor for Civil Engineering 453 this semester. This is an odd semester for us. Normally we have a big group of students in the spring take the class, but we had 6 students who were ready to graduate if they could do the senior design in the fall, so we decided to go with it. Looking at the group, I thought it would be interesting for us to have a multidisciplinary project that was just several different topics all combined together into one project. And the project that we landed on was taking a look at the Enslow Park neighborhood here in Huntington, which I'm sure everybody here is already a little bit familiar with. You've maybe heard of the flooding issues that they've had there. And I asked the students to focus on the low-hanging fruit, which is there are some ways that maybe the resilience of the community's transportation networks can be improved. I think maybe less low-hanging fruit would be actually preventing flooding in the area. I mean, that's maybe not even achievable with the economic and environmental constraints that are in place. But I think there are some things that can be done, and the students have been looking at that since the end of August and are really excited to share with you their findings. A little bit of information about the papers that I've given you. There are forms here that you can write questions in case, and I think it's going to be likely, we run out of time. I've told the students to keep their presentation to 30 minutes, which means we'll have about 20 to 25 minutes for our discussion and questions before we need to leave for the next class that's coming in. So I think there's going to be a lot of feedback you may have that we can't get to today, but I'd like the students to respond to any questions or suggestions you've got. So this is optional. If you want to provide feedback, you can put your name and email address on this form. It's front and back, and I think I've given everybody multiple papers, so I'll just collect these at the front at the end of the presentation. And then the other thing is the rating form where you can provide a numerical evaluation of the student's presentation skills. Again, that's optional. I always find it a little bit distracting if I'm trying to rate so many different attributes while I'm also listening to the presentation. And so if you're like me and you don't think you can split your attention both ways, feel free not to evaluate the presentation quality. We can go back and do that later with the recording if needed. But if you just want to focus on one or the other, totally fine. It's just really whichever you prefer. So any questions about the approach we're going to follow today before the students begin? All right, go ahead, guys.
So my name is Wheaton Riggs. I'm the project manager. As Dr. Wade said, we are looking at the Enslow Boulevard neighborhood. Excuse me, the Enslow Park neighborhood. We wanted to go ahead and define the area for you. So this is Huntington. As you can see down here in the southern end, we have the neighborhood coming right off of Powell Greer. And a little bit of background on the neighborhood. There was a flood back in 2016, and it managed to hit about 2.2 inches of rain. And then we had another storm in 2021 that hit about 3 inches. And then earlier this year, we saw about 3.5 inches of rain. The neighborhood is kind of boxed in by a few mountainous regions on the southern and western side. And the project goals that we wanted to accomplish were to increase the resiliency of the neighborhood, incorporate a little bit of redundancy, and make it not only easier to get out, but also to access. And we wanted to reduce the evacuation time. We planned on doing that by adding a bridge as well as an access road on the southern end of the neighborhood. Some of the things we were excluding by assignment were we didn't want to dam the creek, possibly having a reservoir somewhere upstream. That was excluded from this project. We also weren't planning on dredging the creek. There's some environmental issues as well as property issues. Some of the same reasons that we didn't do a flood wall as well, that going alongside of the stream. We didn't want to have to take people's property or have to mess with the landscape as much as possible. So what we decided to do was split into groups. We had a WMS analysis for our hydrologic team. They got an idea of the rainfall in the area and defined the watershed. The HECRAS analysis was done by the hydraulics team. They were able to give us an idea of the shape of the bed for the stream and then when the intersections are going to flood. We then did an evacuation analysis to understand how long people have to get out, when they're going to be able to get out, or if they're able to get out. We then did a traffic simulation to understand the surrounding areas, the intersections that will be directly impacted by the evacuation. And then, of course, we had a new road design and a new bridge design. And so I'm going to pass it over to Seth, and he's going to talk about our hydrology.
So, for those of you who don't know what hydrology is the branch of science that examines how water reacts through Earth and Earth's surface in relationship to the land. Why do we need to know this? We need to understand how rainfall will affect the neighborhood and how it affects flooding during a certain amount of storm. We need to know how much rainfall will produce a certain flow rate at any given location. We need to analyze the flow rate under the bridge or wherever throughout the basin, pretty much we can analyze it. So some inputs that go into hydrology analysis is watershed area. Rainfall data such as intensity and duration are also included. Curve number, which is a product of land cover and land use and soil characteristics that would be downloaded from the web. All those inputs are ran through hydrology simulations such as NSS and HEC1, which I'll get into later. After they are ran through the simulation, it produces a flow rate versus time graph, or otherwise known as a hydrograph. The software we decided to use for this analysis is called Watershed Modeling System, or WMS for short. Pretty much the software just obtains GIS data from web-based sources and uses the GIS data to compute parameters for the basin. Like I mentioned before, it produces hydrographs and models as the output. Some of the data that was downloaded for our reservoir was Surgo soil data, which is produced by USGS surveys, land cover and land use, which is the National Land Cover Database, also operated by USGS. We assumed a type 2 rainfall distribution curve based off of geographical location, and I'll also go into that more depth later. On the right-hand side are some of the data that was downloaded for the analysis. So the figure on the right is the watershed basin. We placed an outlet location at the current bridge location connecting Enslow Boulevard to the neighborhood. An outlet location allows us to analyze all the water that would run through the outlet. So the black lines you see bordering the basin, any water that would land inside of that would eventually flow through the outlet location. So after delineating the watershed, the software produced a curve number of 68 and a total watershed area of 7,700 acres would flow into the outlet. So this is a breakdown of the curve number calculations WMS performed. As you can see, it is mostly soil type C. Below are the infiltration rates in inches per hour according to the USDA for the various soil types. The below figure is a hydrograph with 40 different runs. Each run had various rainfall intensities over different durations. We used this hydrograph below to kind of pick our design storm, which more accurately represents the rainfall that fell on the basin during the May 2022 storm. So the design storm is shown, the hydrograph of the design storm is shown in the bottom right. It has a time to peak of 140 minutes and a 140 minutes from increasing intensity to peak intensity as shown in between the green vertical lines. Like I mentioned before, it is a type 2 curve shown in the bottom left. This is based off of geographical locations, and you can see according to the top right map, West Virginia is in the type 2 region, so the software went ahead and assumed the type 2 curve. So the design storm we chose is a 24-hour duration with a recurrence of 25 years, meaning that once every 25 years, the neighborhood is likely to experience the storm that we simulated. After the simulation, it produced 4.26 inches in 24 hours, and at the outlet location at the current bridge, it produced 2,300 cubic feet per second flow. In the news article at the top right, according to National Weather Service in Charleston, it indicated 3.5 inches. Our simulation produced 4.2 inches. So our simulation is actually an overestimate of what occurred during May 2022 to improve factor safety and to over-design the system. So to further justify our 2,300 cubic feet per second, we ran a National Stream Flow Statistics simulation, or NSS. The difference between an NSS and HEC1 simulation is NSS does not use basin-specific data. It uses more generalized location data to simulate the basin, as where HEC1, you got to download the data specifically for just your basin. So after running the NSS simulation, it produced 2,100 cubic feet per second. So we went ahead and decided to use the 2,300 cubic feet per second to design our storm based off of that flow rate and that inches per hour over 24-hour design period. So I gave the flow rates and the hydrograph to William to let him do a hydraulic analysis on. So I'll go ahead and turn it over to William and let him tell you about what he did.
Hello, my name is William, and I performed the hydraulic analysis for the project. Hydraulics is the study of a water system network, and for this project, Pole Creek was the network that was studied, specifically the region that flowed through the Enslow Park neighborhood. The data input into the analysis was a hydrograph and the WMS results, and this data included the flow rate per 15-minute time intervals for a 24-hour storm. The results from the analysis was the water surface elevation, and this was used to determine the depth of the water for each intersection location in the neighborhood. And then these steps were used to determine the flooding for each intersection location. This was provided to the evacuation section to do their analysis. HECRAS was the software used to perform the hydraulic analysis. HECRAS can perform 1- and 2-dimensional unsteady flow analysis. Results from this analysis can be water surface elevation, flow area, or velocity of the flow, and depths. These can be displayed graphically or through tables or visual representation. First, the 2D model was developed, and the purpose of this was to have a visual representation of the flooding. And terrain data was the first thing to be obtained from the USGS Earth Explorer and was inputted into the model to develop the terrain, which you can see on the right. A map layer was then placed onto the terrain to visually indicate where the location of the neighborhood was, and a land coverage data was imported from NRCS Data Gateway as a layer and map layer. And each soil designation had a mains and value inputted for those. The watershed shapefile from the WMS results was inputted into the model to develop a 2D mesh layer. The different geometric components were added, such as break lines and refinement regions and in and outflow boundary conditions to introduce an exit flow. The WMS hydrograph data was inputted as the unsteady flow to perform the analysis. The 2D results were then developed for the unsteady flow analysis, and the results were observed in a RAS map or the command window. And each intersection that appeared to flood was determined based on these results. The HECRAS 2D results, each intersection that was labeled A through L was determined to flood based on the 2D results. And the water surface elevations and depths for each of those locations was determined based on the 1-dimensional model unsteady flow analysis. And it was found that intersection K did not appear to flood based on this analysis. The HECRAS 1D model was then created after the 2D was finished, and the LiDAR data was obtained from the USGS resource, the same as terrain from the 2D model. And this LiDAR data was compressed, decompressed, and merged using LAS tools program and imported into Open Roads Designer to develop terrain. The terrain, the geometry components were then drawn in the terrain model. The center line of the stream was drawn in cross sections and then exported and imported into HECRAS. Once the terrain was, or the geometry was developed, the 3 bridges that are currently in the neighborhood were modeled inside the geometry. The 3 existing bridges were considered the existing model, and the proposed bridge was implemented into another geometry along with the 3 existing to develop the proposed geometry. The mannings and roughness values were then inputted for the left of bank, the right of bank, and the center of the channel. And these are referenced from HECRAS user manual and the Army Corps. Ineffective flow areas for the expansion and contraction of flow from the bridges was implemented from the cross sections upstream and downstream of the bridges. And since the terrain was developed from LIDAR, it appeared that there was no elevation below the water line, so the bathymetry data had to be developed. So an Army Corps HECRAS model was referenced and used to determine these elevations below the water line. And field measurements were done to determine if the cross sections for the Army Corps study matched the conditions in the site. Once the one-dimensional unsafe flow analysis was complete, a software program called Viewer was used to determine the elevation for each intersection. And the cross-section for each intersection location was determined. And the water surface elevation for those cross-sections was, for each 15-minute interval, was subtracted by the intersection elevations determined, which was used to find the depth for each 15-minute interval. Once the water exceeded the banks to when it reached a depth above half a foot was the time frame in which the flooding occurred or would occur for the existing and proposed conditions. The National Weather Service was referenced for the depth constriction because based on them, they say that once the water exceeds half a foot, the roadway could potentially cause damage to the vehicle or loss of control. Here's a table of the results showing each time of flooding for locations A through K bridges. And it was found that based on the results, the proposed condition caused location F to have a decreased time of flooding by 15 minutes based on the constriction flow from the bridge. I then provided this information to Wheaton to perform his evacuation analysis. And
All right. So we want to know whether or not people are going to be able to get out of this neighborhood. We also want to know how long they have, and we also want to make a simplified model of the neighborhood so that we can do that analysis. So to start, we graphed the flood times for each of the intersections. As you can see, the time 0, however, was considered the first bank flooding. We wanted to use that because most people aren't going to just start evacuating the second it starts raining. There has to be some sort of queue. And so we said, okay, once the banks flood, we're starting our time. We made an assumption of 1 vehicle per household. After going through the neighborhood, we saw that there were some abandoned, possibly condemned, or state-owned houses. So we knew nobody was living there. So we made the average assumption of 1 vehicle per household. That ended up being 292 vehicles. We also included a 5-minute prep time so that people can see the water, get their stuff, get in the car, and then start their evacuation. And so to model the neighborhood, we split it up based on the intersections that were going to flood and ones that were going to be most impactful for people getting through them. And as you can see, section D does include some of the roads that go on high elevation and sort of circle up around the neighborhood to the southern side. So our simplified model here, I'll explain it just briefly. The red dashed lines represent our intersections. The blue squares represent the sections, and then the arrows represent the flow of traffic. I decided to take it into increments, starting at time 0. As you can see, the total number of cars in each section. After 40 minutes and the traffic moving to each section, we were able to get everybody out of B, as that is the time it takes for it to flood the intersection, gaining access from B to A. And then, unfortunately, at time 55, intersection B does flood. Intersection B is rather crucial. It connects both D and A to section E. So 41 vehicles, unfortunately, were unable to get past the intersection in time, leaving them stuck behind that half a foot design criteria. So we implemented our new design exits. Down on the southern side, that is the proposed road. Of course, that's connected to intersection K. It fortunately does not flood, so people are able to get through that one rather easily. We shuffled a lot of the traffic volume to that area. Up here in the middle, it's a little hard to see. I have an arrow pointing to it. That is the proposed bridge. That's rather a lifesaver, as most of the vehicles end up going into section A and can now be split off into 3 different sections. As you can see, after time 40, we were able to get most of the vehicles towards the exits. And then at time 55, which was our previous crunch time for the intersection B, We were able to get everybody past those intersections that flood and in a new section to then go off into the existing intersections that surround the neighborhood. With this analysis, we were able to determine that everyone is able to successfully leave, assuming it takes everyone that incredibly long time to get through each intersection. And so in conclusion, we went from 41 vehicles unfortunately being left behind, intersection B, to now having everyone able to successfully leave. And in doing this, we're also incorporating a lot of redundancy into the neighborhood by allowing emergency services to have better access, such as fire, EMS, and police. And so now I'm going to pass this off to Dylan, and he's going to give us an idea of our traffic.
Hi, I'm Dylan Sawyers, and I did the traffic simulation. So for this, we need an understanding of how efficiently people can evacuate, and will people be met with delays, or will the traffic flow? And do these added exits improve overall resiliency? And does the level of service go up when you add more exits? So for the simulation, we used PTV Bistro, and this software forecasts delays, queues, and displays the level of service. And simulations were done for the current and the proposed design. So here is the traffic data input. We have volumes, road geometry, and the signal timings, and then we use the Bistro to output the queue lengths, delays, and the level of service. So for past traffic data, a past study was done on Hal Greer and Washington Boulevard in 2018 on a weekday. And this data was gathered by Ferguson Nyepel, which is a firm located in Columbus, Ohio. They found that the peak hours for the morning were 7:30 a.m. to 8:30 a.m. and the peak hours in the evening to be 4:30 p.m. to 5:30 p.m. We had no past data for the Enslow exit intersection, and so new traffic counts were done based on these peak hours found at the Washington Boulevard and Hal Greer intersection. So for the traffic counting data, we used a jammer counting board, and 2 counts were done for each intersection, considering the AM and PM peaks, so 2 for PM and 2 for AM. And all these counts were done in November on a weekday. For the simulation assumptions, we assumed that people are heading towards the interstate and 1 car per household. So no flaggers to direct the evacuation and no cars are entering the neighborhood. And all these evacuators are leaving at uncoordinated times. So for the current condition results, we found that the Enslow intersection exit operated quite adequate with a level of service B and C, but when they approached the intersection, the Hal Greer and Washington Boulevard intersection, they're met with very bad queue times. So the level of service would be E and F for the AM and PMs. And for this proposed design, you can see that the original exit is less stress, and those level of service for the Hal Greer and Washington Boulevard goes down to with much less delay. And all these new exits have adequate level of service, with the bridge exit having level of service B and the new road having A. So overall, what is improved? Overall delay has gone down for the evacuation through Hal Greer and Washington Boulevard by 42% for the AM and 75% for the PM. And the new bridge exit has a level of service B, which is adequate, and the new road exit has both approaches having a level of service A. Overall, these new exits add improvement to how efficiently people can evacuate. And now I'll pass it off to Jacob for our proposed access road.
So my name is Jacob Simpkins, and I designed the access road for our project. So this access road was designed in order to bridge these 2 existing roads in the area, which will give Enslow Park a new access point to Hal Greer Boulevard. This location was chosen due to the low flood risk in the southern portion of the neighborhood, and this design does not interfere with any houses in the neighborhood or other existing structures. It is also designed on state-owned land. So here's a closer look of the drawing, which I created in Civil 3D. You can see the path that the road will take in order to reach this adjacent section to the neighborhood. And this green line represents the border of the embankment that would be needed for this road. So I based this design off AASHTO standards and assumptions made based on the area's geometry. So AASHTO states that a typical lane will have a width of 12 foot and a shoulder width of 3 foot on each side. And AASHTO also states that the maximum grade for a road should be between 7 and 12%. Assumptions made during this design were that the maximum speed limit would be 25 miles an hour. The lane depth of the road would be 1.5 feet, and the shoulder depth would be 1 foot. We are also creating an embankment with a 2-to-1 slope. As you can see, this cross section that shows where you can visualize the geometry of the road and the proposed embankment at this elevation. Here's a profile view I created of this road, which compares the proposed road elevation and the existing ground level. This also shows that the maximum grade of this road would be 9%, which is compliant with the AASHTO standards specified. The earthwork required for this road would be largely fill, requiring about just over 56,000 cubic yards of soil for the embankment. And the cost of this would be roughly $1.2 million. This cost is based on pricing given to us by local contractors here in Huntington, West Virginia, and it covers the cost of soil, delivery, paving, and the equipment. I also created an alternate design for this access road, which serves the same purpose as the previous design, with a new access point to the road that will lead to Howard Boulevard. The benefits of this alternate design is that there will be less overall earthwork required, which will make the material expenses a lot cheaper. The downside is that the road will be longer than the previous and will have a greater change in elevation. There is also concern that this design may interfere with existing structures. As you can see here, this road gets very close to Huntington Termitology, but currently this design doesn't actually disrupt the building, and this red line represents the cut that would be required for the embankment. Profile view is also created for this alternate design, where you can see that the existing ground level would now be above the proposed road elevation and would show a maximum grade of 15%, which would not be within the AASHTO standards that we specify. Now I'd like to pass this on to Zach Bishop, who will be covering our bridge design.
Okay, so as a group, we were told that we had to add a bridge somewhere in the neighborhood, and then after visiting the neighborhood, we knew that it had to be some kind of entrance or exit, since there's only one current entrance and exit. That leaves people in the bottom part of the neighborhood kind of a long ways from the exit. So we know we need to add another bridge that's an entrance or an exit to improve resiliency. So then the question of where are we going to put the bridge? Our first option was location A. We chose this because it has 3 roads connecting into it. This will help like funnel people into it to get people quicker and then they can leave to get on Calvary. But once you look at the location A's slope, how much the ground elevation changes, it was coming up to like a 20% slope the bridge would have to be to leave Enslow and then get on the Calvary. That was kind of not plausible. So then we moved further downstream to location B, where the slope is more gradual and almost non-existent. So we ended up choosing location B, which has a slope of 1%, so pretty negligible. Has ample room for approaches both on both sides. So we used a program called eSpan 140 that takes into account different inputs such as the length of the road, width, how much traffic is going to be driving on it each day, and the speed. And then it gives you what kind of steel beams and steel bridges that would fit your specifications. So typing all that stuff in for our requirements gave us, we needed the W36 by 210 beam that has a depth of 36 inches. So then with that, you get a hydraulic opening underneath the bridge of 533 square feet. And then once we got this number, we were wanting to see if there's any way to improve that to allow more water to flow underneath. Because once the water hits the bridge, it'll go over the bridge quickly, making it impassable. So we started thinking, if we added a pier in the middle of the bridge, that would allow us to have shallower beams because the pier is taking some of the weight. So then cutting our bridge length in half to 40 feet and then running another eSpan model, so we could use a W21 by 93, which would have a depth of about 21 inches, so it's a lot less. And that gave us an area of 607 square feet. So it's more than the 506 square feet, but then when you think about the restrictions, the hydraulic restrictions the pier adds, as far as the water hitting the pier and having to slow down there, and then also branches and leaves getting caught with the pier, and the alterations to the stream bed the pier would have to have with putting concrete and installing the pier, we decided it was not worth a slightly bigger hydraulic opening. So then we started thinking about steel versus concrete, if concrete could give us more strength with a shallower depth. So the length of our proposed bridge will be 82 feet. And then using this table that's pictured here gives us the minimum depth using different types of bridges. So if we were going to use an adjacent box beam, you multiply the length by the factor there, and it gives us a minimum depth of 2.5 feet for the concrete bridge. And then the same for the steel, give it 2.7 feet minimum depth for the steel bridge. So theoretically, concrete would give us the ability to have a shallower bridge. So then we ended up choosing an adjacent concrete box beam. The East Bend gave us that we needed a W36 by 210, so we chose the next closest concrete beam to that, which is a 33-inch pre-stressed concrete box beam. The dimensions are shown here in this CAD file. It'll be 33 inches deep and then 33 inches long. So if our bridge width is going to be 33 feet, we'll need 10 box beams, and then that's allowing a small amount of space in between each beam. And then we chose the adjacent design instead of the spread design because the beams will be closer together, giving us more strength with smaller beams. Here's a CAD drawing. This was gotten from the West Virginia Department of Highways and then altered slightly to fit our specifications. The drawing had seven beams, and we've changed it to 10. So the cars will be driving from left to right on the bridge, parallel to the green lines, and then the abutments are on both sides. And then the pink dashed lines are steel beams, or steel bars that will be going through the bridge and then tightened on the outside to keep the bridge together and keep it straight. And here's just a cross-section view of what it will look like with the guardrails on there. Again, you'd be driving sort of into the screen and then having 10 beams going through there.
So, after implementing those new roads and the bridge, we were able to improve some resiliency. We were able to work in a little bit of redundancy and safely be able to get people in and out of the neighborhood. And thank you. I apologize. This is our reference slide. I'm sure everybody wants to go through that very quickly. And then thank you very much. Is there any questions?
All right, thanks a lot, guys.
So we've got about 20 minutes for questions, and Wheaton, why don't you go ahead and manage that, call on people as they've got questions. And
Everybody but Dr. Nicholas. Y'all want to come over here? We can take the first question.
The slide numbers are covered up by the task force, so that's gonna work.
I got a question.
Yes, sir.
I've been in the neighborhood several times, and a lot of homeowners give me anecdotal evidence or anecdotal comments that the developers in that park changed the flood paths, the flood routes. You have any knowledge of that, or did you hear that, or
So,
what do you think about that?
so where we placed the outlet was at the current bridge location, and Connect Park is downstream from that, correct? So,
Upstream.
it's upstream, so if it did, it would have incorporated it into the soil type coverage and stuff was from 2011 USGS data reporting, so depending on when the construction was, it is.
All right, thank you.
Yes, sir. I had him up first. I'm sorry.
You did a cost benefit analysis on the road. Did you do one on the bridge about cost estimates about how much it would cost?
Hand that off to you, Zach.
Yeah, you want to do it?
Yes, we did. The DOH gives bid sheets on how much, and it kind of it sort of specifies how much the bridge itself would cost per linear foot. So we could get a rough estimate on that, but it was sort of unclear. And it was done on previous projects. So it'll have if a bridge was built last year, it'll have the cost per linear foot of that bridge. It was we were unsure of what all that included, the per linear foot. Is that just the bridge, but just the steel? Is that with the whole bridge with the concrete, you're driving on asphalt and everything, is that construction prices, is that filling in the land? So it was kind of unclear, so we just left that out at the end.
How much was it with the data that you did find?
For the steel, it was about 300,000, and the pre-stressed concrete box being about 280,000.
We've got some folks from DOH here. Do either of you happen to know whether?
That's why we left it out.
What you want to do is going to be more complicated than that. So the average unit bid price, you're looking in the right place, but you need to look at a whole bunch of stuff. So all those things that we pay contractors for, down to nuts and bolts and pounds of steel and clearing and grubbing and all that stuff would have to go into that. So it ends up being a fairly detailed list and maybe beyond the scope of what Dr. Wade might have anticipated for this. But that's how you would go about it.
Okay.
So you've got unit costs for all sorts of little, every single component of what goes into the bridge.
Right, now for the bridge, a lot of times we'll, like for planning stage, we'll look at a cost per square footage of bridge, and I can't remember what the number would be currently for this scope of bridge, but there's a number you could have gotten from our bridge designers that probably could have gotten.
And then that's like an overall cost, like an overall number.
Yeah, and that would account for your substructure units and all the materials that build
That
the
would
bridge.
count for
It
everything.
wouldn't be your site stuff, and it wouldn't be Jacobs Road as well. It'd just be the bridge. The road, of course, you just want earthwork volumes and square or tons of asphalt is really the two biggest drivers there.
Right.
Yes, sir.
Did you happen to look to see if you were in a flood zone?
Yes, sir. I'm sorry, I don't think we did.
It is in the flood zone.
We are, but I don't remember if we had it.
Yeah,
I
most-
personally hadn't checked.
Most of the whole thing is in the flood zone. Of course, like the road on the top is not, and then the very last road, the houses on the opposite side of the road are not right on the edge, but yeah, the whole thing is in the flood. Yeah.
Remember what zone it was? Was it modeled? What, you said you got a HEC-RAS model from the Army Corps?
Yes.
Says probably a zone AE. Did you happen to look at a comparison between the backwater with your proposed bridge versus the existing situation you had in whoever did the HEC-RAS model?
You're like 45, it went from Howard's to 45.
Yeah, I'm not really talking about in time of the peak of hydrographic flooding the roadway, but just in, say your design storm was 25 that you picked.
Yeah.
Did you look at what the 25-year elevation would be beyond your proposed bridge with the addition of the bridge?
Not beyond the
Not beyond.
neighborhood. Check that. I just looked at the geometry of the HEC-RAS model. That was the only thing. They run a simulation on it.
So your parameter for your whole goal was to see what elevation you had to be above to get people out quicker. Okay.
I got maybe 2.5 questions here. I'm just curious, would this bridge be a structure that's open permanently such that it may have some impact on traffic flow on How Greer? Or would it be one that's just kind of gated off and opened only in emergencies?
We just have plans to have it open full-time as a new access to the neighborhood.
It's 2 lanes wide, but on the exit to Hal Greer, you can only go out towards the interstate.
You can go right.
Yes,
Yeah.
because it has the grass median there. You can pave the median there.
What about impacts to people cutting through the neighborhood then to use that new bridge? Of course, it's probably not much gain there, but just a thought.
Yeah.
The other thing, just about, you guys made some site visits, right? Went out and did some ground truthing. Did you do any ground truthing? And I'll ask it about 2 different things. As far as your vehicle count, I know you guys said you assumed 1 vehicle per house. I'm thinking of some houses there are rentals and things. You're probably gonna have a couple roommates and such. I don't know how many empty houses are in there. I'm not driven to the neighborhood.
I had about a handful.
Just a handful?
No more than, we couldn't certify that there was more than that.
Okay.
We tried to get a census data to see whether or not, just see how many people in the neighborhood to do it more accurately, but we weren't able to get the data.
Let's say transportation is not my expertise. I'm more civil environmental side planning now, but the 1 per house sounds a little low to me. 2 may be high, but probably 1 sounds a little low. So it may impact things some. And my other thought was on the rain gauge, and I get it, the closest rain gauge is at Tri-State. You didn't have one right there, so you're probably talking what, 10 air miles away or so. Did you guys do anything as far as ground truthing with your hydrographs to see, if it showed, hey, you're gonna have this much water at this place, and talk to any locals or see any wet marks after that May? Probably not right after the May flood, because you guys worked this the fall, I get this, but talk to the locals and find out where the water actually was versus where your hydrograph showed it would be.
Unfortunately, we did not talk to any of the locals. I think that would have been really beneficial. But we didn't do that.
Jacob does know people that live in
So
there.
I've talked to people, I have some family that lives in that area. They actually live on the other side of Fort Pole, closer to where the last problem is.
My only thought was, you had, I forget what you said at the airport, but if you had a cell that dumped more water there 10 miles away, you may have altered several things for you.
Well, we also used rainfall intensity, like radar kind of.
Okay.
Current, what it was.
That's the thing I may miss part of that, because I was trying to.
Well, we didn't really mention it either, but we used that to verify the inches fell during the duration.
Okay, good deal, thank you.
Regarding your bridge question, like the transportation side of it, we just assumed that it was a stop sign rather than adding like a full signalized intersection, just to to make it more simple. And also, I assumed a stop sign as well because the intersection, the Calgary and Washington Boulevard intersection is not very far from it. So I don't know how much impact it would be by adding another signalized intersection at the bridge.
Yeah, you're probably not gonna have a whole lot of people cutting through the neighborhood as a shortcut, because you're right, 'cause it's what, quarter mile to the intersection, and you hit that 45 zone, as soon as you turn. So, okay. This is a curiosity more than anything. Okay, thank you guys.
Any other questions?
This is Dave.
What made you choose 25-year for your designs?
That would.
So,
correct that.
we more or less used previous radar data and news articles that stated 4 inches of rain fell in 24 hours. So we knew the storm didn't obviously last 24 hours. So we kind of used the news articles of 4 inches in 24 hours to justify our flow rate at the end. That's pretty much the only resources we had, that and NOAA with the rainfall intensity, but that's pretty much all we had. And with the number we selected, we figured it was a pretty decent overestimate of what was on May 2022 value.
I've been asking questions for
4 years.
Well, I have a couple here. You did 2 different hydrologic methods. You used the NSS, and you also went into great detail on the WMS. Can you tell me what is NSS? Where does it come from?
So
It doesn't have input data much, right?
So NSS is a hydrologic, it's like NSS is ran through WMS and it's a model for rainfall. So NSS doesn't incorporate like soil type coverages or land use or curve numbers or anything like that. It just uses, so you're in Huntington, say they did a study over in Charleston, so they used geographical similarities through, so you're in Huntington, they did a study up here, they kind of incorporate what is in your surrounding area. They don't get into depth as H1 simulation does with the soil types and land cover uses.
What's the one input parameter for an NSS model?
NSS does not assume ponding and pooling. It doesn't assume you have a dam or there's a big pond on the hill or anything. It assumes free flow state throughout the entire simulation.
But what number goes in the equation?
Just basin area, pretty much. And it uses geographical similarities between different studies to predict.
So you're in Huntington, did it use the Ohio equation or the West Virginia equation? Or did it compare both?
I'm pretty sure it used the West Virginia because we had to download the data for Cowley County.
Which West Virginia equation? There's 3.
Eastern Dam, or no, Western Plateau.
All right, thanks. Yeah. Bridge guy, how wide are concrete box beams?
Concrete wide, they're 3 feet, 36, I think
Okay.
one we're doing 36 inches wide and then 33 inches deep, so slightly thicker.
Yes, sir.
So how reasonable is it to assume that all the residents can actually see the water exceed the banks from their houses?
It's not very reasonable. When we're doing the evacuation analysis itself, we're using the time it takes for them to flood the intersection, and it's obviously not going to take everyone 40 minutes to get past it, but they have up to 40 minutes. And so the idea is more so just to see whether or not people are going to get through the intersection, if it's even possible, within that allotted time. And so I apologize. What was your question? I might have started.
Basically, we're just wondering, you gotta see the water to know it's rising.
Absolutely. And so that whole period of 40 minutes, or so to speak, for one of the intersections, it incorporates then that randomness, because everybody's not going to leave at the same time. Nobody's going to, like you said, nobody's going to see it at the same time. So I just wanted to do the analysis on, this is it. This is all the time you've got. And so make your mistakes, but if you can manage to get through there, get to the intersection within the criteria that I've set aside, then you'll make it through as far as that goes. So it's not overly specific, but it's kind of trying to incorporate as much randomness into it as possible. And I'm sure you've got a traffic question, Dr.
Me? A traffic question?
He's converted.
I don't know about that. I have a construction question. On the access road, I was just curious, two things. Maybe I missed it. Was labor baked into the numbers on the estimates?
It was, labor was included with the soil cost, the delivery, and the paving.
Okay, and do you have any idea how long it would take?
Do not. We assumed that would be more so up to the contractors and how big the workforce was.
That was.
So the amount of time that you looked at for when the existing bridge flooded, is that you had a hydrograph. Did you find out how long the bridge would be underwater? Like, how long of a time would the people have to wait, say? I mean, do all of them really need to get out? What am I trying to say? It's like, what's the time interval that their only way out is inaccessible?
So the way I modeled sorry for flipping through this really. So the way I had modeled, apologize. The way I had modeled it, it turns out that up towards the northern section, it takes the longest time to flood, 70 minutes, and each section before it actually is less time. I picked those intersections specifically because the other ones tend to flood at the same time, and they have much more time because it's further into the neighborhood. These are the intersections much closer to the river that runs through the neighborhood, and so you'll see those flood last. So they actually had more time to get through. As long as they could get through certain intersections, they still had time to get through the other ones. And I just sort of took it in increments as to which ones will flood. Including the time 40 for this intersection over here, the section B, it really is kind of secluded, and they also only have one access to get to section A. And the same thing with C, they only have one way to get to A, so they're going to be filed into that direction, and they'll end up getting cut off, assuming the rate at which they're crossing the intersection is that full 55 minutes. And the total number divided by the total number of vehicles. So it's very much a huge estimation because typically you're only going to see vehicles cross an intersection in a couple seconds. But this is assuming close to like a minute per vehicle in some cases. So this is very much, people are flooding to the intersections, people are all the way in there and they are trying to get out.
My question was really about how long their way out was underwater.
Oh, I see.
Did you look at that?
Not too much. I mean, it would just be until the water recedes, which, I mean, like the one this past, I mean, it was like a couple of days, I think.
Okay.
I apologize. I misunderstood your question.
It'd just be until the water recedes and however long. I don't know how long it was until it receded for the previous one.
Are you talking current conditions or proposed conditions? Because proposed has the new access road out the back that never floods, so they still have an exit.
Yeah, I guess I was talking about existing conditions. Like, could the people up in C, which is really high, if it would go up and come down in about an hour or so, they would need to leave all.
And then up in D, there's very high elevation. It's the highest elevation housing in the neighborhood, and it kind of comes up towards the southern end, and they'll get cut off immediately with section or intersection B. So that is a good point. We never thought to think after how long they're going to be stuck with the flooding.
Based on my model, 24-hour duration, it still was over the redway a good amount, so I'm not sure what would be past that point. So,
Your model was only 1D, right?
yeah.
So you'd have to have that, your model was steady flow condition.
They're unsteady flow.
Unsteady. You need unsteady flow model to see, okay, it comes up, it comes down.
Still
Just
just
too much over.
We've got time for one more question before we need to part ways for today. Who wants to take the honor of the last question? I think Andrew's got it definitely.
I don't want to steal Sean.
No, let's do both. One from Sean, one from
No, I
Andrew.
was just wondering about your zero time when you pull the trigger to get an evaluation or an evacuation. And if you considered like an early warning system.
We absolutely did. We actually looked into, I forget the specifics, but it's kind of like yes,
So
absolutely, please.
it's like you can attach it to a bridge parapet wall and it sends a beam down and measures water depth, and you can set it to a certain depth that it will send a signal to somebody to issue a warning. So that's what we looked into, and also like same thing, but you set it on a bank. But really, we were leaning towards the sonar on the bridge parapet wall.
Oh, thanks.
We got a question from someone who called in. Josh asks, please describe some of the sensitivities conducted in the hydraulic modeling. I'll probably I'll put that on a feedback form since we're out of time. That's something that I'll allow you to get back to Josh on. Andrew, you got a quick one?
So mine was related to Sean's. My question was just gonna be, what happens if the storm hits at night? So people are gonna not see the water exceeding the banks, and I'm also confident that not every house can see the banks.
This was, the evacuation model was assumed day. But the traffic analysis was for both AM and PM. So we do know what it would look like outside of the neighborhood during the day.
But it was more focused around more, how do people know?
Yes.
Yeah, you can still use the sonar thing. You can just send a signal to whoever you're charging.
All right, well, thanks again, everybody, for being here today. If you'd like to give us your numerical feedback on the students' presentations or those question forms, I'd be glad to take those now, or if you need some time to fill it in and you want to send it to me as an email, that's fine as well. But really appreciate you being here.
Could I get a link?
Yeah.